Hello, welcome to another integrity lecture, and in this one we're going to begin the discussion of a case study from the Visual Six Sigma book, which I'm asking you to read. And this is based upon a Six Sigma project I was involved with a number of years ago with a company whose actual name we will not reveal. But we'll discuss the case study, and in doing so, we will work through all stages of the DMAIC cycle. So this will allow you to work through an entire project, and along the way, I'm going to start filling in with lots of supporting materials as we use different statistical methods and quality methods. We'll jump out here and there and talk about how these methods are actually used. In this particular case, we're going to begin. I'm going to give you an overview of the case study, show you how some of the quality tools have been used in the define phase, and then we're going to start a discussion of an important issue called measurement capability, or MSA. Here we go. So again, this is chapter 6 of the Visual Six Sigma book. So again, you can begin reading it, and as you read the case study, you do not have to become bogged down in all of the details on jump usage. Really just read through and get an understanding of the problem the team was facing, and in fact, at this point, you only need to read the case study to the top of page 181. Okay. And I'm just going to give you a little bit of background. This is a company, we'll call it Components Incorporated. They manufacture these aluminum parts. They're actually aluminum heat sinks that go into these very expensive speakers for home entertainment equipment. And I mean very expensive. And these aluminum heat sinks are visible to the buyer of the speakers. Therefore, the surfaces of these heat sinks must be aesthetically perfect. Again, very expensive equipment. And what is wanted on the surface of these heat sinks is a very smooth, rich, black surface, a very dark, rich black surface, no blemishes whatsoever. Unfortunately, Components Inc. in its manufacturing problem is having a great deal of difficulty with part quality, to the extent they may lose a very profitable business if the problem isn't fixed, hence the need for a Six Sigma project. Okay. And what they're doing, they take the aluminum parts, and aluminum, frankly, is quite susceptible to corrosion, especially oxidation. So there's a process called anodizing, which is a process in which the aluminum substrate is actually coated with an oxide layer, and that oxide layer actually provides corrosion protection against corrosion or oxidation of the underlying substrate. And this particular process is called type 2 anodized. This is actually very common for aluminum material, and it's done in a sulfuric acid bath. Basically, you clean the parts, you suspend them in the bath for a certain period of time, and the parts become anodes, hence the term anodized, and then this oxide layer is allowed to build up. Okay. And on slide 7, just a quick schematic of what the process looks like. So you clean the parts, and in this case, the etch and desmut steps were not necessary. You clean the parts, you anodize them in a bath, and then subsequently the parts are dyed they're supposed to be, again, a deep, very rich black color. Anodized surfaces actually have a lot of micropores in them. It's inherent to the process, so it's not unusual to dye the surface or provide an additional corrosion coating on top of the anodized surface. And in our case, they're going to apply a black dye. Now, because of these micropores, the black dye actually seeps down into the micropores due to capillary action and then dries and adheres to the surface of the part. Okay. Basically, a pretty simple process. Okay. So, again, in the define phase, the first thing we want to do is put together our project charter. Okay. So in this case, the problem statement, again, is the key part to this, the problem and goal statement. So currently they are running very low yields. In fact, you'll see later they're averaging about 19%. As a result, they have high levels of scrap and rework, and they're running very big backlogs. In other words, the parts are of such poor quality they just can't ship enough of them, and in the last 6 months they figure they've lost about $450,000. The customer's unhappy and is ready to pull the business from the company. So what is the goal? The goal is to improve the anodized process from 19% to 90% by December. And the key performance indicator is the lot-to-lot yield, and we'll plot that on an individual control chart. Okay. So the project scope is only limited to the black anodizing process. So steps before or after anodizing are actually out of scope for the project. Again, I like to start with a very high-level SIPOC model. I'm not going to go through the whole thing with you, but you can see here's a typical use of it. And here is an input-output process map, which gives you a good idea of how the process flows, what the process step variables are, what the measured outputs are at each stage. And one of the things that's of interest, by the way, these inputs at the different steps, currently most of this information is not being tracked, so the team is going to have to implement a data collection strategy to try to collect information on key process variables. And of course, you can do a cause and effect diagram. Again, you can read through these. I'm just illustrating the use of these tools. And by the way, we're going to focus initially on measurements. In other words, there was a suspicion that some of the problems might be with the measurement systems. We're going to see, yes, there were some issues, but it didn't really explain the extent of the quality problems. But initially, we're going to talk about those measurement systems and how we evaluate them. Okay. And I want to explain the responses, or the critical to quality characteristics. Okay. So these are the CTQs. Okay. There is actually 4 of them. 1, the thickness of the anodize, and then 3 parameters of the color, and they're commonly called L star, A star, and B star. This is actually very common in many industries where they measure color. And you can read all about it if you want to. I give you a little bit of background on slide 13. But a spectrophotometer is set on the surface of the finished part, and the spectrophotometer takes the color on the surface and maps it into a 3-dimensional space. And in that space we measure L star, a measure of lightness and darkness. Lower values indicate darker color. A star, a measure of red-green. Okay. So positive indicates red, negative indicates green. And then a third is B star. This measures yellow to blue. Again, positive indicates yellow, negative indicates blueness. So you're going to see later that these end up being critical to quality characteristics or responses that we're going to measure on the parts as they're manufactured. In fact, we'll use these as responses in a designed experiment later on in the improve phase. Okay. Now, the anodized thickness, L star, A star, and B star, again, are the critical to quality characteristic. However, there's also a visual inspection. In other words, a trained technician actually inspects the parts and grades the surface quality into 3 categories. One is a purple to black color. This is, by the way, unacceptable. Normal black, this is a good part. This is a nice, deep, rich, unblemished black surface. And then there's another category called smutty black. This is actually a black but very much smudged and sort of ugly looking surface. So only number 2 is acceptable. Okay. Category number 2, the normal black colored parts. Okay. And the anodized thickness, by the way, we won't get into a lot of technical detail, is measured by what is known as a beta ray backscatter gauge. You don't now have to know about the physics of it, but it's a fairly common method for measuring thin coatings on metallic surfaces. And a lot of questions abound as to how good this gauge actually is in terms of measuring thickness, and also how good are the inspectors or technicians in actually properly grading the parts into the 3 categories. Okay. As I mentioned, we saw the cause and effect diagram, and they were listed out quite a number of variables, and because of that they put together a data collection plan. And I'm not going to go through all the details, but basically most of this data was not regularly being collected. So they instituted a plan to start collecting it, and later we'll see some of the data that was actually collected. So basically this process was not being monitored very carefully at all, which is, you'll see later, is part of the problem with the poor quality, why they had it. Okay. So basically they've put together their data collection plan, settled on the variables they want to collect the data on. Again, these are typical defined phase activity. And they found there was a lot of data that didn't exist. They'd have to start collecting it. So that leads us from define into the measure phase. But in the measure phase, one has to begin by asking questions about the quality or validity of the measurement systems. If we're collecting data, or even data has been collected, can we trust the data? Is it of sufficient quality for us to use as part of the project? This leads to something in Six Sigma commonly called Measurement Systems Analysis, or MSA. This in itself is a very big topic. We're going to talk about it with a relatively narrow focus, but all too often in trying to carry on research and development or carry on continuous improvement, there is a tendency for people to put too much faith or trust in measurement systems, especially systems that have never actually been evaluated to see what their actual quality actually might be. Okay. So we're going to talk about measurement systems analysis in general, and then we're going to relate it directly to the case study. Okay. And we're going to break the measurement systems analysis up into 2 parts. What we call continuous MSA, that's where we evaluate a measurement system that makes continuous measurements. Example, the backscatter gauge to measure thickness, and actually the spectrophotometer to measure the color readings. Well, there's also a type of MSA that deals with attribute systems. Basically, these are systems in which the measured characteristic is nominal or categorical. So in the case of this project, the visual inspection and grading of the parts is called an attribute measurement system. In other words, no continuous measurements are taken. It's basically they're inspected and somebody sorts the parts into the three categories. And attribute measurement systems are notorious for capability issues. So the team, looking forward, has to evaluate the measurement systems and decide if improvements are needed or are the systems good enough as they currently exist. Okay. So what we need to do is to go forward with some MSAs. By the way, the team had looked at the spectrophotometer quite a number of times and determined that it was capable for what it does, and they elected not to pursue any further evaluation of it. Okay. However, they did want to look at the backscatter gauge, and they did want to check the capability of the visual inspection. So what I'm going to do is, before showing the results of these studies, we'll actually cover some notes, okay, where we'll talk about methods and terminology used in continuous MSA, and then later we'll talk about them with respect to attribute MSA. So at this point, start reading Chapter 6, and you'll notice you have a copy of these notes, and I've also supplied notes on continuous and attribute MSA methods, which we'll now go ahead and cover.